Dobrze, to może
Okej.
zacznijmy w takim razie. Witam wszystkich na naszym cotygodniowym seminarium Katedry Akustyki. Witam przede wszystkim panią doktor Karolinę Kluk, naszą absolwentkę, a obecnie światowej sławy badaczkę procesów słyszenia z Uniwersytetu w Manchesterze. Doktorat robiła u profesora Mura w Cambridge, także naprawdę jest to osoba, która ma duże doświadczenie. W większości tutaj z Państwa Karolina jest bardzo dobrze znana, więc nie muszę wyjaśniać, natomiast mamy, widzę, doktorantów, profesora Nawrocika, naszego Nestora, także kilka słów się należało tutaj wyjaśnienia. Karolina od wielu lat prowadzi badania z zakresu psychoakustyki, zajmuje się i podstawami, i ubytkami słuchu, zrozumiałością mowy, także te zagadnienia związane z psychoakustyką są przez nią bardzo dobrze eksplorowane, a dzisiaj opowie nam po angielsku ze względu na to, że pracuje od wielu lat po angielsku, coś na temat hearing, hidden hearing loss i hidden hearing. Także Karolina, the floor is yours. Jeśli ktokolwiek będzie mieć pytania, to zostawmy je na koniec, chyba że, tak jak mówiłem, będzie to pytanie niecierpiące zwłoki. Proszę się zgłaszać, podnosząc rączkę i wtedy ja udzielę głosu, przerwę na chwilę Karolinie. Także proszę bardzo, Karolina.
Super, dziękuję bardzo i dziękuję za zaproszenie. Jest naprawdę, to jest moja przyjemność tutaj prezentować. Chciałam też podkreślić, że magisterkę robiłam u profesora Senka, także tutaj jeszcze więcej połączeń. No więc tak, po pierwsze przepraszam, że będę mówiła po angielsku, ale no jest mi znacznie łatwiej mówić po angielsku, kiedy prezentuję moją pracę, także zaczynam w takim razie po angielsku, ale jeśli macie pytania po polsku, to bardzo chętnie je przyjmę po polsku, mogę odpowiedzieć po angielsku, spróbuję czasami po polsku, ale to może być trochę pomieszane. Okay, so from hidden hearing loss to hidden hearing. I thought I'll talk today a lot about my hidden work. So let's start with the hidden hearing loss. Well, in recent years, animal studies have shown that noise exposure may actually result in loss of connections between inner hair cells and auditory nerve fibers. So this schematic figure here shows a representation of a healthy, well-functioning inner hair cell with really nice, good connections between the fibers of the auditory nerve and the inner hair cell. Here are really nice intact synapses that ensure good connection between the fibers of the of the auditory nerve and the inner hair cells. Now, so let's have a look what happens when a person is exposed to noise or an animal. So noise exposure causes loss of synapses. Basically, the synapse connections swell up and burst, and basically we are losing the connections between the fibers of the auditory nerve and the inner hair cell. And over time, because those fibers are not stimulated, the connections are gone, the auditory nerve fibers actually start degenerating. Now, this degeneration and the loss of the auditory nerve fibers in animals have been shown to be leading to cochlear synaptopathy and hearing loss associated with that. Now, in humans, it has been really difficult to actually measure the cochlear synaptopathy on this hidden hearing loss using pure tone audiogram. Now, this is the reason why we're calling it hearing, because in clinical terms, normal hearing is anything that is better than 20 dB HL across frequencies from 250 to 8 kilohertz. So in clinical terms, normal hearing is pure tone audiometry or detection of pure tone across frequencies up to about 20 dB HL, which doesn't necessarily mean that our hearing is absolutely perfectly normal. It only means that it meets the clinical criteria for normal hearing. So what are the consequences of this noise exposure? So let's have a look at, first of all, the electrophysiological consequences. So we know that noise exposure causes loss of auditory nerve fibers. Now, the loss of auditory nerve fibers will result in increased central gain, will result in deficit in temporal coding and deficit in intensity coding. So all those deficits now will have consequences for psychophysical performance. So they will lead to poor interoral phase discrimination, poor frequency discrimination, and poor intensity discrimination. And as you can imagine already, all these psychophysical measures or performance on psychophysical measures will also have real-world consequences. So this all will lead to poor sound localization, poor perception of speech in noise, and poor music perception. And of course, loss of fibers of the auditory nerve also results in hyperacusis and in generation of tinnitus. So in theory, it all sounds really nice and clear and consequential. But what happens in real world is, of course, quite a bit more complex. So we thought, okay, let's look at measures, possible measures of this hidden hearing loss or of cochlear synaptopathy in humans. Can we detect it? Can we measure it? Can we use it to predict what is going to be the effect of huge noise exposure on humans? So first of all, we looked at electrophysiological measures, and we found that the best electrophysiological measures from animal studies that were sensitive to cochlear synaptopathy were the amplitude of wave 1 of auditory brainstem response, which is basically the marker of the function of the auditory nerve, and the envelope following responses. Now, in terms of psychoacoustic tests, the tests that seemed to be the best candidates were amplitude modulation detection, interoral phase difference discrimination, frequency difference limits, intensity difference limits, and auditory localization, as well as complex behavioral tasks like speech perception in noise. And finally, from the more objective tests, some studies showed that middle ear muscle reflex could be used as a marker in animals, at least, for cochlear synaptopathy. And we wondered whether also functional magnetic resonance imaging could reveal some changes in the auditory pathway due to noise exposure. So now I'm going to show you results of 5 related projects that we conducted over the 5 years. And this was our first big MRC program grant, which is now being continued for another 5 years. And maybe in the discussion, I'll mention the project that we are running now, but it's still ongoing, so I cannot present the results of that one. But anyway, so let's have a look at those first 5 projects. Altogether, we tested almost 400 participants. They all were young, healthy people, students, and they all had normal, clinically normal pure tone audiometry. So please keep that in mind, that we excluded anybody who showed any level of hearing loss, most likely at higher frequencies, so at 6 and 8 kilohertz. So they all had straight, flat audiograms. And we measured ABRs, EFRs, psychophysical measures. One study looked specifically at fMRI, so I'll show you results of all of them. Now, in some of the measures were exactly the same across 5 studies, so you can see actually combined data from all 5 studies, while others, like for example, only the fMRI, was used only in one study, so it was a smaller sample of 60 participants. Still, I think quite a big sample for MRI study. Right, so what did we find? Not that much. So first of all, we were really surprised that we did not find any significant relation between wave 1 ABR and lifetime noise exposure. So all participants were asked to estimate lifetime noise exposure for us. We spent almost 2 hours talking to them about their experiences, how many times they go to nightclubs, how many times they went to loud music concerts, what their work environment is, whether they listen to music via headphones or speakers, how loud they set it. Basically, we tried as best as we could to estimate their lifetime noise exposure. We did it using the NESI questionnaire in the format of interview. Now, so if you look at individual wave 1 ABR amplitudes, here you have the amplitudes on the y-axis. So this is the wave 1 amplitude here, and on the x-axis is the lifetime noise exposure. Blue are males, orange are females, and as you can see, it's pretty much a scatter plot. There is really no correlation, no relationship here between the wave 1 amplitude and the noise exposure. In another study where we specifically looked at experiences of tinnitus, there might be some tendency for males to show larger, going actually in the opposite direction. So males showing a larger amplitude of wave 1 ABR when they had a larger noise exposure, which doesn't really make much sense. And females going in the correct direction, but the results were not significant. They were only the trend. So it's possible that it's just random. So overall, the message is wave 1 amplitude of ABR doesn't seem to be a very sensitive measure of cochlear synaptopathy in humans. Now, when you look at the amplitude of envelope following response, again, exactly the same. There is pretty much the correlation between the lifetime noise exposure and the amplitude of EFR is very close to 0, as you can see here. With middle ear muscle reflex, again, it's completely different picture to what we are seeing in animals. In animals, you see very good MEMR being a very good marker of cochlear synaptopathy. We are not really seeing it in humans. Speech perception in noise, really not much effect. And finally, MRI. We thought that we might be able to see some differences between two groups of 30 individuals who were most noise exposed. So the orange dots here in this case show results for individuals, for 30 individuals who had highest noise exposure. And the blue ones show results for the individuals who had the lowest noise exposure. And on the x-axis here are the different stages within the auditory pathway. So we have cochlear nucleus, superior very complex, lateral lemniscus, inferior colliculus, and finally up to auditory cortex. So we thought if we think about the damage happening already at the level of the auditory nerve, then you will probably be able to see a difference between the two groups at the level of cochlear nucleus. And as you can see, these two dots are very, very close to each other. So there is clearly no difference at all. And this lack of difference continues throughout the whole auditory pathway. So that was really disappointing. But what we found was that actually people with larger lifetime noise exposure tended to be more likely to report tinnitus. So as you can see here, we had two groups of participants, again, all with normal hearing. And people, group with tinnitus showed much higher lifetime noise exposure than people without tinnitus. So it seems that tinnitus might be a good marker for huge lifetime noise exposure. But again, so what is going on? So what we found altogether was that there was no clear evidence that lifetime noise exposure in young adults with clinically normal PTA is associated with reduced auditory nerve function, that it might be associated with reduced performance, and no changes in sun-evoked fMRI activity. So what happens is maybe that noise have the capacity to induce hidden changes leading to tinnitus, but we found no evidence that cochlear synaptopathy is one of those changes. So that was slightly disappointing. I mean, so much work went into it. And in the end, we said, well, you know what? We really are not finding anything. So go and enjoy loud music. But at the same time, we know that work-related noise exposure causes hearing loss, right? Later in life, people do get hearing loss because of noise exposure. So how do we detect this very, very first signs of noise exposure? And why are we not being able to detect it? Also, we thought okay, one of the reasons for the fact that we cannot find this good markers for the early effects of noise exposure in humans might be because of the differences in the design and in the populations between animal studies and humans. So remember that most of the evidence comes from, for synaptopathy, comes from animal studies. And animals, when they are exposed to high sound levels for experimental purposes, they are raised in complete silence. So they're raised in very quiet environments. And then their ears are blasted with loud sounds. And of course, they show the loss of synapses and synaptopathy happening there. But that's not reality. That's not how we live, right? We are not raised in complete silence. We are all exposed. So there was one study by Kujava and Lieberman where they actually did do that. So they actually raised the animals not in complete silence, but in sort of in background of sounds and music happening and different noises. The sound levels were moderate, not very high, but moderate, but very ongoing. And then they exposed the animals to this big blast, and they noticed that actually the size of synaptopathy was much, much smaller than in animals who were raised in complete silence. And this raised the idea of potential conditioning of our ears, of our hearing. I like to think about it in terms of, or sort of compare it to as conditioning of skin. Like when we go outside into the sunshine after the whole winter and our skin is pale and not very well used to sun rays, we go outside and spend a whole day in bright sunshine, we burn immediately, right? But if we actually dose our exposure slowly, after a week of small exposure, we can actually spend the same amount of time in the bright sunshine and actually not burn immediately. So it sort of feels like there might be something similar happening with our ears. So to test this hypothesis, we ran a study looking at exactly that, looking at the effect of conditioning on our hearing. And this idea of conditioning was already mentioned by Canlon in 1988, who suggested that prior exposure to prolonged noise at moderate levels can actually condition the cochlea and reduce its susceptibility to noise trauma from a subsequent intense exposure. And later in 2002, they also clarified their definition of conditioning versus toughening, saying that conditioning results from long duration, moderate level, non-traumatic exposure, while toughening results from repeated high level exposures, where each of them causes temporary threshold shift. And temporary threshold shift is basically change in the audiogram from before the exposure to post-exposure. Now, this data, we are now in the process of writing it up, so it's still hot. I cannot even say off the press yet. It's just hot off the collection. So what we did, we recruited 52 participants. They all were 20-year-old, well, around 20 years old students who already bought tickets to attend loud music events at Manchester Academy. So basically they were going to concerts. Among them, we also managed to recruit 17 pairs. So people were going together to the same event and were going to spend the whole time together at this event, which basically meant that we knew or were quite certain that they would have exactly the same noise exposure during this one concert. So we could see whether the same noise exposure would cause exactly the same change in their PTA, in their hearing. So we measured standard audiometry, standard PTA, extended frequency PTA, audioacoustic emissions, distortion products, normal, standard, and high frequency. We asked them about their experience of tinnitus and estimated their noise exposure in the 10 weeks leading up to the concert. So we were interested in this conditioning effect. So we wanted to know how much noise they were exposed to for those 10 weeks before they attended the very loud music event. The idea being that if they were spending the 10 weeks in very, very silent environment, they may be showing bigger effect of the blast noise exposure due to music. And then people who actually spent those 10 weeks listening to music, but not at very high levels, but still being exposed continuously to some conditioning, and then having to attend loud music event, their ears would have been conditioned and potentially would show smaller change in the function. So let's see what we found. No surprise here. We found that post-concert, their PTA has increased, so they had temporary threshold shift. From before concert, here shown in blue, to post-concert, shown in orange. So you see that the average shift in PTA was about 15 decibels. Now, we were surprised to see that actually their extended high-frequency audiometry did not change. So there was no shift. So it means that, which means that their ears were not affected at high frequencies by this noise exposure. So this is extended high frequency, 14 kilohertz. What was very clear was the change in their tinnitus perception. Here on the left-hand side, so the left-hand side column shows the reports of tinnitus before the concert. So most of them, about almost 50% of people showed, almost 80% of people showed that they had no tinnitus. Very few showed very quiet tinnitus, and just few individuals said they had loud tinnitus. But post-noise exposure, post-concert, there were actually quite a lot of them who said that they had either very loud or loud tinnitus, loud moderate tinnitus. Very few had no tinnitus. Now, also not surprising probably is that the attendance of concert resulted not only in the change of PTA, but this change or the size of change in the PTA or the size of the temporary threshold shift was related with the change or with the type of tinnitus. So here on the y-axis is the post-concert increase in tinnitus. So we were looking whether at change in tinnitus, so whether it changed from, so if it changed from no tinnitus to very loud tinnitus, then the change was very large. And as you can see, if people had PTA change of 20 to 30 dB, then they definitely had very large change in their tinnitus. However, people who had even very small change in PTA here, say only about 5 dB, they could still have really large change in their tinnitus. So again, very interesting relationship and very interesting showing that tinnitus is really quite a good indicator of some effects of noise exposure on hearing, but we are really not there yet to fully understand what that effect is. Anyway, let's finally have a look at this conditioning effect. So this figure shows the effect of conditioning versus temporary threshold shift. So on the x-axis is the measure of conditioning, which is this cumulative noise exposure over the 10 weeks before the concert, versus delta PTA. So this is change in the PTA, which basically shows the TTS. And although the results didn't reach significance, what we're seeing here is the trend in the right direction. So people with low noise exposure in the 10 weeks before the event show larger change, larger difference, or larger temporary threshold shift than people who had quite large noise exposure, and they showed a bit smaller change in their PTA, so smaller temporary threshold shift. So this sort of follows the idea that if you're exposing, you're conditioning your ears before a big blast, then maybe your ears are a little bit better prepared to deal with the big exposure, and you don't actually end up with massive TTS. Now, what was interesting also, what we found was that there was clear sex difference between in terms of the size of the TTS between males and females. Again, the difference didn't reach statistical significance, but you can see that it's clearly there, and going in the sort of expected direction, with females having TTS about 3 decibels smaller than males. So what is happening, and what did we find? So summary, we found that attending loud concert resulted in large shift in PTA, so quite large temporary threshold shift. In modest shift in audioacoustic emissions, I didn't show them here, but it was also measurable. We found increased reports of tinnitus and no shift, to our surprise, in extended high frequency audiometry. We found also substantial TTS, so temporary threshold shift variability between pairs of participants. And those are the pairs that, as I said, were attending the concert together. We knew that they were standing next to each other, and yet they didn't experience the same size of TTS. And this is pointing to individual differences. So the individual factors play also a huge role in how we react or how we respond, how our ears respond to noise exposure. So although the results were not statistically significant, there were trends that aligned with conditioning and with the sex hypothesis. So we expected that people who had more conditioning would have smaller TTS, and we expected women to have smaller TTS. Now, why women were expected to have smaller TTS is because of female sex hormones. Now, this brings me to the next project, which is this time research done by my PhD student over several years. And she looked at 6 sex differences in auditory function between men and women. Now, so what do we know about sex differences in hearing? We know that young women tend to have better hearing than young men. And we know that there is a clear role of female sex hormones, and specifically estrogen, on hearing in Turner syndrome, where women don't make estrogen. And in animal studies, during high levels of estrogen, which is the breeding season, it seems that female show better hearing responses. So whether it's female mice, fish, birds, or frogs, when estrogen is high, hearing performance, hearing function seems to be better. So we decided to explore that further, looking specifically at the role of estrogen. And interestingly, from animal studies, we also know that there are estrogen receptors in the cochlea. And the role of estrogen was shown in the development of auditory system, which aids the neural excitation in the inner ear. We know that estrogen also acts as neuromodulator in facilitating the perception of auditory signals. And it also plays a role in protecting from damage. So females' ears are protected more from noise exposure, it seems, than males, at least from animal studies. And it plays a role in protecting the ear by delaying the onset of age-related hearing loss. Now, progesterone, on the other hand, is working almost in the opposite direction. Worse hearing sensitivity is reported during periods of high progesterone level. HRT with progesterone seems to be associated with reduced hearing sensitivity and with lower OAEs in postmenopausal women. And in pregnancy, when progesterone levels are very high, there are also suggestions of increased incidence of tinnitus and negative influence of progesterone on auditory function and on balance. So just very quickly, I'll remind you what is the menstrual cycle and how we can divide it. So basically what we have throughout the menstrual cycle of the 30 days, what happens in women is that the 2 hormones, well, there are more hormones, but the main hormones that we were focusing on were estrogen and progesterone. And they almost work against each other in the opposite directions. So in the first phase of the cycle, we have early follicular phase, where both estrogen and progesterone are quite low. Then we are moving to the second phase, which is just before ovulation, and that's where estrogen level is high, and then it drops post-ovulation, while progesterone level is staying low. As we move post-ovulation, progesterone level starts increasing, estrogen stays quite low and slowly increasing, but it's definitely relatively much lower than the progesterone. And finally, just before the period, both levels start sort of leveling out and stay low throughout until the new cycle starts. So basically what we are having is the follicular phase is the one where estrogen is dominating, and luteal phase is the phase where progesterone is dominating. So what we did, we've performed first a systematic review to look at the measures of auditory function and how they relate to different points in the menstrual cycle. So we looked at two effects. So first effect was looking at the comparison between premenopausal women and men, so basically reproductive age, young women and men. And what we found was that there were loads of reports of women actually having better PTA, better OAEs, better ABRs, speech perception, and so on. That was not the case in postmenopausal women, who tended to have steeper decrease in hearing sensitivity than men. And then we looked also at how hearing changes in the month. So depending, which could potentially be related to the dominating or dominant function of, or dominant role of estrogen versus progesterone. And what we found was that, again, most of the measures showed better performance during this first phase, the follicular phase, when estrogen is dominating, than the second phase. So this is a brief summary of the auditory measures that we reviewed and how they change throughout the menstrual cycle. And as you can see, that sort of the up here means that the performance is better, down performance is worse. So all measures except ABRs seem to be better during the follicular phase when estrogen is high than any other phase. Interestingly, ABR seems to be better at the time when progesterone was dominating. Now, so this was a nice systematic review, which sort of gave us very good basis for the experimental work. Summarizing, we know that premenopausal women have better hearing, or should have better hearing function than age-matched men. Premenopausal women have better hearing sensitivity during follicular phase. Postmenopausal women tend to have steeper decreasing hearing sensitivity than age-matched men, and there is a fast and rapid decline in hearing sensitivity at high frequency soon after the start of menopause or in postmenopausal women. So we conducted two studies to look at two effects. So first of all, to look at the effect of those changes within a month, and secondly, to look at changes postmenopausal, so comparing young women before menopause to postmenopausal women. So in the first study, we tested 35 participants. We had 20 young women, again at the age of around 20, and 15 men. Now, all participants attended weekly sessions and performed number of measures. So we measured their OAEs, we measured their TIMS, we measured their PTAs, asked them to do speech perception and noise, and just noticeable differences in intensity. On top of that, women also gave us blood samples every week. So we took blood from their arms and we measured their estrogen, progesterone, luteinizing hormone, and follicle stimulating hormone at those weekly intervals. because we wanted to make sure that we had really accurate measure of their hormones and not just reports saying, well, yeah, I think I'm in this phase of the cycle, but I'm not sure. So here's a summary of their blood, of their hormone levels. And as you can see, they're nicely fluctuating, with estrogen being highest at the, so having here now a big peak around the ovulation, and then second one post-ovulation, and progesterone riding at the second phase. Okay. So results, PTA. As I said, we tested men and women at weekly intervals. So we covered 5 weeks to make sure that we covered the whole cycle, and we repeated that. So really, each person was in the study for 10 weeks. So what you're seeing here is that for men, their PTA, this one is, for example, at 4 kilohertz, didn't change much throughout the 5 weeks of repeated measures. So this is week 1 to week 5, their PTA stays very flat. Now, in women, on the other hand, when you look at their performance at the PTA from week 1, which is the week at early follicular phase, when the estrogen starts going up, but it's still quite low, to week 2, which is very high estrogen, week 3, estrogen is falling down and falling down. You see that the best performance, or the best PTA, is in week 2, when estrogen is highest. So that's quite interesting. And the difference is of about 5 dB, which is not non-significant at all. Then we also looked at extended high frequency PTA. And again, men show pretty flat performance, while women show, again, best performance in week 2 at early follicular phase, when estrogen is highest. Then we looked at just noticeable differences in intensity, thinking that if their PTA changes, if women's PTA changes due to estrogen effect, then most likely this will also translate into changes in the intensity discrimination. And this is exactly what we saw. So we saw this sort of change in the intensity discrimination, but here it sort of doesn't seem to be occurring exactly at the, yeah, it is sort of at week 2, but also at week 5. So it's the time when estrogen starts picking up again. The effect is not as huge, but what is interesting is that you're seeing decreased performance at the time when progesterone is getting high. And then finally, speech and noise. In speech and noise, we didn't see any effect. I think the test is just not sensitive enough to pick up those small differences that are happening in our hearing throughout the month. Now, then we ran a second study where we compared postmenopausal women with premenopausal women. So this time we had 21 postmenopausal women, age 50 and mean age of 50, with 20 premenopausal women with the mean age of about 20. And again, we performed all exactly the same measures and measured their hormone levels at weekly intervals. So here on the left, you see the results, the hormone levels of women, postmenopausal women, at 5 weekly intervals, and you can see that they all are very much the same, very, very low. The same goes for progesterone. Postmenopausal women have very low progesterone level, and premenopausal women have peak at luteal phase in progesterone. So let's have a look at the PTA, audiometric PTA. Postmenopausal women, again, just a flat line, just exactly the same pattern as what you saw in men. Completely different to premenopausal women, where the hearing was fluctuating. And the hearing threshold is increased, so now it's at around 20 decibels. So it's not all the way low down at around 0. This is an example of 12 kilohertz PTA, extended high frequency. Again, completely flat line, but increased. So this may be related to age, may be related to loss of estrogen. Who knows? But postmenopausal women show a degree of hearing loss at extended high frequencies that actually doesn't fluctuate at all throughout the whole month. The same went for just noticeable differences in intensity, hardly any fluctuations, sort of really the measurement error for postmenopausal women, different picture to what we saw in premenopausal women, and no effect on speech and noise. So overall, what we found was indeed confirmation that estrogen seems to have a protective effect on hearing, or aiding effect on hearing in women. So we found that in premenopausal women, they had better hearing, better PTA than men. They had better extended high frequency PTA than men, and they performed better than men in J&D, specifically with improved performance during the period of increased estrogen, so early follicular phase. So great, right? So women are protected from, have protection from estrogen. So as long as you are young, you can enjoy loud music, enjoy yourself. So let's enjoy some loud music. So then the question comes, why do we like loud music? Why do we enjoy loud music? Some researchers suggested that musicians, although are aware of adverse effects that loud music listening can have on their hearing, they often choose not to use hearing protection. And musicians report obtaining actually more satisfaction from listening to music without hearing protection. So what do we do with that? And why? Well, one of the reasons that for enjoying loud music may be the hedonic response, so the response where actually our auditory system interacts with the vestibular system, and this vestibular activation occurs following stimulation of the same pathways that are connected with the reward centers in the brain. And because of the emotional involvement, it sort of mirrors the effect of addiction. So in another PhD project, my student looked at number of questions related to differences between musicians and non-musicians. And we argued that if there are those differences between in auditory performance and in preferences between musicians and non-musicians, maybe they are actually driven by vestibular system and not necessarily only by auditory system. So what we did in this experiment, we tested almost 100 musicians and almost 100 non-musicians. So we had almost 200 people in our study. They had very similar PTA. So you see here a summary audiogram up to 16 kilohertz for musicians in orange and non-musicians in blue. So in fact, the non-musicians had slightly better hearing at high frequencies than musicians. And what we asked them, so we hypothesized that if musicians prefer to listen to music at higher sound levels than non-musicians because of this increased response and increased pleasure from music. They actually want to have it presented at higher sound levels to allow the sound to properly stimulate their vestibular system. So vestibular system, we know that starts responding to sound levels that are quite high, above 80 dBHL. Anything below that, and mainly at low frequencies, so at around 500 hertz and lower. At higher frequencies, we don't really have much response from the vestibular system. So we argued that if we are thinking that this enjoyment from music comes from this interaction of the auditory system with vestibular system, then musicians should be enjoying or should be wanting to listen to music at even higher levels than non-musicians. So what we did, so we had our 200 participants, we played them 6 music pieces, and we asked them to adjust the amplifier volume control or sound level dial as high as they wanted until they reached the level that they really enjoyed. I mean, of course, we had some limits to protect them from overexposure. Here are the 6 different pieces of music that we use. We use them from the digital music library, freely available online. And we basically covered 6 different genres. I'm not going to try or to attempt to play them for you, but if you want them, I can share them with you later. So what we found was that indeed, musicians preferred their music to be presented at higher sound levels than non-musicians. The difference was of about 7 decibels, and it was very consistent. So that was great. So musicians prefer listening to music at higher levels than non-musicians. But that doesn't mean that it is because of the involvement of the vestibular system, right? So in the next slide, I'm going to show you why we think it may be the involvement of the vestibular system and how we measured it. Now, why we think it might be the involvement of the vestibular system is because when you think in evolutionary terms, the cochlea and the vestibular system are anatomically connected, and they used to be just one organ. So in many fish and amphibian species, the vestibular organ, which is the saccula and the utricle, they are important not only for balance function, but also for detection of sound. And in humans, we can also show this sound sensitivity of the vestibular system by evoking the response from the vestibular system using sound. And we can measure that response of the vestibular system to sound by vestibular evoked myogenic potentials. And this is what we did. So we measured vestibular evoked myogenic potentials in our participants. So we used 500 Hertz tone bursts presented at high sound level, and we recorded VAMPs. So we recorded 3 VAMPs from each of the participants to look at the amplitude of their response. And what we found was indeed a difference, significant difference in amplitude of the vestibular response between musicians and non-musicians. And this is really pointing us in the direction of this hidden hearing. So we are hearing not only through our auditory system, but when the sound level goes high, we get this contribution from the vestibular system to enable us to enjoy this loud music and to get additional enjoyment, not only auditory in terms of hearing, but overall pleasure from hearing this loud sounds, or being really annoyed by the loud sounds. It sort of goes in both directions, whether you like it or not. Now, what we were disappointed about was that actually the size of this amplitude of the vamp did not predict the size of or how loud people really liked their music to be played at. So I think that was a bit disappointing, but it doesn't mean that it's not there. Basically, we found that vamp amplitudes were not very good predictors. And I think personally that probably vamp thresholds would have been a better measure of vestibular function and have better chance of being the predictor of the music listening level preferences. So that's basically for the next project. So to summarize, we seem to enjoy loud music, but it remains unclear whether it is because of our hidden vestibular hearing. So here we are, from hidden hearing loss to hidden hearing. And I just wanted to acknowledge financial contribution of all those funding bodies and everybody's help. And that's all. Thank you so much.
Za wspaniałe wystąpienie, dużo bardzo ciekawych rzeczy.
Let's see, maybe did I stop sharing? No, I didn't.
Yes, you did.
Yes. Okay, już przestałam. Dobra. Okej. Jakieś pytania?
Dobra.
Dziękuję.
Dokładnie. Tak, czy są jakieś pytania? To może ja zacznę, bo mi się nazywa kilka. Przede wszystkim jedna uwaga, jak się mówi się zawsze, że jeden rysunek mówi za 1000 słów. Naprawdę super wizualizacje, podziwiam za pomysły na te wizualizacje wyników, bo naprawdę dużo wyjaśniały za pomocą jednego rysunku. Super.
To jest część, która zawsze zajmuje najwięcej czasu, nie? No,
dokładnie tak.
Cieszę się, że to zadziałało.
A pytanie jest takie, jeśli mówiłaś o podziale na mężczyzn i kobiety, czy w ogóle jakieś wytłumaczenie ewolucyjne, oczywiście kobiety, progesteron, estrogen i tak dalej. Natomiast czy ma to jakieś uzasadnienie ewolucyjne, to, że kobiety mają lepiej słyszeć niż mężczyźni?
Wiesz, to myślę, że tak, że jeśli byśmy spojrzeli na to właśnie z ewolucyjnego punktu widzenia, to myślę, że to ma też duży sens, bo jednak jeśli chodzi o rozmnażanie, prawda, chcemy, żeby kobiety, nie wiem, znalazły najlepszego partnera, który jest najlepszym kandydatem. Czyli one też muszą być w stanie go dobrze usłyszeć, zrozumieć co powie, jak powie, żeby wybrać tego najlepszego. Trudno powiedzieć, czy to tak działa u ludzi, bo jednak teraz nie pamiętam dokładnie, kiedy to był opublikowany artykuł, ale to był artykuł Sary Collins, która zrobiła eksperyment bardzo ciekawy, bo zrobiła zdjęcia kobiet i mężczyzn, i poprosiła ich też wszystkich, żeby przeczytali ekstrakt z książki i ich nagrała. I najpierw pokazała, to było wszystko zrobione na studentkach. Najpierw pokazała grupie dziewczyn zdjęcia tych chłopaków i powiedziała, ok, ocencie ich atrakcyjność. No i tam dziewczyny dały jakieś tam znaki atrakcyjności tym chłopakom. Potem puściła im właśnie te ekstrakty z książki, które czytali i też powiedziała, a teraz ocencie atrakcyjność ich głosu. No i dziewczyny oceniały. No i się okazało, że w sumie głos, dziewczyny stwierdziły, że głos, który był taki najbardziej niski i spokojny, był najbardziej atrakcyjny, ale niestety to się nie pokrywało ze zdjęciami. I też patrzyła też na wzrost. I tak samo ze wzrostem, że po prostu wiemy, że niski głos niekoniecznie się pokrywa z fizycznymi charakterystykami, nie wiem, symbolami osoby. Ale w drugą stronę z kolei mężczyźni zrobili to samo dla kobiet, czyli najpierw widzieli kobiety, oceniali je, taką atrakcyjność, a potem oceniali atrakcyjność dźwięku, atrakcyjność głosu. I mężczyźni byli znacznie lepsi, jeśli chodzi o takie połączenie, że jeśli kobieta była dla nich atrakcyjna fizycznie, to tak samo też miała atrakcyjny głos, chociaż no, nie wiedzieli. Także no, może u ludzi to się tak do końca nie pokrywa, bo wydaje mi się, że większy wpływ ma na to, co mówimy, niż to, jak brzmimy, jaki mamy głos. U zwierząt jest to bardzo, bardzo duży efekt. U ptaków widzimy, że jednak ta wokalizacja, czy te piosenki ptaków, im bardziej skomplikowana, im lepiej brzmi, tym lepsza jest taka tak zwana fitness tego ptaka i tym większe ma możliwości, że będzie wybrany. Także zależy, jak daleko chcemy iść z tą ewolucją, nie? Myślę, że jak spojrzymy na ptaki, no to wygląda na to, że no faktycznie na ptaki, na żaby, im lepiej brzmi akustycznie, tym lepszy kandydat. U ludzi chyba nie, a zdecydowanie nie u studentów.
No to chyba pozytywny wniosek jest taki, który powiedziałaś, że jednak to, co się mówi, ma znaczenie. A drugie jeszcze mam pytanie, bo tego akurat zupełnie nie znam. Jak się mierzy te
wępy? To są te vestibular evoked myogenic potentials. Nakłada się elektrony na szyję, bo to jest mierzone od mięśnia, czyli trzeba napiąć mięsień i mierzyć. To jest taki odpowiedź refleksowa, czyli jak puszczamy dźwięk do ucha, dźwięk w momencie, kiedy aktywuje układ równowagi, powoduje kurczenie tego mięśnia tutaj. Teraz nie pamiętam nazwy tego mięśnia. W każdym razie to jest mięsień tutaj na szyi, powoduje jego kurczenie, no i widzisz odpowiedź, to jest odpowiedź z mięśnia, a nie odpowiedź nerwowa, czy tak jak robimy to z głowy, nagrywania EEG. Także to jest po prostu mierzenie refleksu. kiedy układ równowagi powoduje skurczenie mięśnia. No i u ludzi wiemy, że to jest przede wszystkim w niskich częstotliwościach, właśnie około 500 Hz to jest taki sweet spot, najlepiej nasz układ równowagi odpowiada na ten dźwięk. No i musi być dosyć głośny, no bo na niższych poziomach ten układ równowagi jednak się nie włącza. Ja mam przygotowane kilka slajdów też na temat tego wępa i właśnie tego, jak on się dołącza do dźwięku, ale to może na następne wystąpienie.
Pewnie. Na pewno byśmy chcieli więcej, więc jak najbardziej zapraszamy do następnego wystąpienia.
Już się prosiło,
Czy są jakieś pytania? Czy są jeszcze jakieś pytania? Zachęcam, podnoszenie rączki działa. Honorata.
Ja mam pytanie, czy macie w planach, albo czy mierzyliście, bo tutaj była mowa o kobietach przed menopauzą i po menopauzie, ale u kobiet po menopauzie, które suplementują hormony, czy ten efekt będzie to również działał protekcyjny na słuch i jak gdyby będzie to kolejny argument, żeby na przykład stosować takie terapie?
Wiem, dokładnie tak samo myślałam też. To jest super pytanie i bardzo, bardzo trudny eksperyment do zrobienia. Bo już mierzenie, w takiej sytuacji trzeba też brać próbki krwi. I reakcja na te hormony i to wszystko to jest bardzo trudne. W tym momencie mam kolejną studentkę, która patrzy na związek między hormonami i tinnitusem i właśnie w tym zakresie skupiamy się bardzo na kobietach wokół menopauzy, które właśnie zaczynają używać tej hormonal replacement terapii. Komplikuje się tutaj sytuacja też tak, że każda kobieta będzie używała inny poziom tych hormonów. Mogą mieć wyższe lub niższe dawki estrogenu i jeszcze potem nie tylko estrogenu, ale estrogenu względem progesteronu. Także to jest dosyć skomplikowane, no ale idziemy w tym kierunku, idziemy i zobaczymy, co dalej z tego nam wyjdzie. Także zdecydowanie w tym momencie patrzymy nie tylko na słuch jako taka pure auditory function, tylko też jako tinnitus, nie? Że tinnitus się zmienia, bo bardzo dużo kobiet właśnie też mówi, że zaczyna mieć tinnitus, jak wchodzą w okres menopauzy i że ta hormonal replacement therapy, gdzie estrogen jest dominujący, powoduje obniżenie tinnitusa, czyli pomaga, czyli najprawdopodobniej pomaga ze słuchem i przez to redukuje tinnitus. No ale tak naprawdę nie mamy żadnych dowodów z żadnych eksperymentów na ludziach. Ze zwierząt tak, ale nie z ludzi.
Super, dzięki wielkie i bardzo, bardzo ciekawe wystąpienie. Super.
Dziękuję. To co, mam was wszystkich puścić już na lunch?
No Jeszcze poczekajmy chwilę. Ja tak sobie myślę, że teraz są terapie dla mężczyzn odnośnie prostaty oparte na żeńskich hormonach. No, może też tinnitusa powinni niektórym mężczyznom leczyć też w oparciu o któryś z hormonów.
Dobrze byłoby ich sprawdzić, nie? Chociaż. No.
Dokładnie. Ewa?
Chciałam powiedzieć, że strasznie mi się podobało.
No dziękuję.
Że mam o czym myśleć. Ale takie pytanie, tam w jednym z tych badań mieliście kobiety przed menopauzą i po menopauzie. I a propos hormonów w tej postmenopauzalnej grupie, sprawdzaliście, czy one biorą HTZ, czy nie?
Tak, braliśmy próbki krwi od nich co tydzień. Także to nam wiedzieliśmy, że miały bardzo niski poziom hormonów. W ogóle te eksperymenty były zrobione w czasie COVID-u, w czasie lockdownów. I moja studentka była z Arabii Saudyjskiej i akurat przed lockdownami pojechała do Arabii Saudyjskiej i już nie mogła wyjechać. Ale w sumie dobrze się to wszystko złożyło, bo kobiety tam nie używają za dużo hormonalnej pigułek i tak dalej. Także te młode dziewczyny w wieku 20 lat były idealnymi kandydatkami do naszego eksperymentu, bo w Anglii na przykład, żeby znaleźć kobiety, które mają, nie wiem, między 18 a 22 lata i nie używają żadnych hormonalnych środków, naprawdę nie jest wcale tak łatwo. No a tam znaleźliśmy bardzo fajną grupę i to były pielęgniarki, które pracowały w szpitalu mimo wszystko, także też nie bały się igieł i nie bały się dawania krwi. No i tak samo te starsze kobiety w wieku około 50 lat, które przechodziły przez menopauzę w Arabii Saudyjskiej też automatycznie nie dostają jednak tych hormonów. Także mieliśmy bardzo, że tak powiem, czystą populację.
Fajno, dziękuję.
Bez żadnych dodatków hormonalnych.
Strasznie mi się podobało, dzięki.
Dziękuję.
To jeszcze jakieś pytania? Nie widzę.
Nie.
Okej. To jeszcze raz bardzo dziękujemy. Naprawdę super
Dziękuję
wystąpienie
bardzo.
i dużo nowości, dużo ciekawych
Super.
rzeczy, zupełnie takich, które są nieoczywiste na pierwszy rzut oka czy ucha w tym
Dziękuję bardzo.
rozumieniu. Więc naprawdę super.
No to dziękuję.
Dziękujemy w takim razie.
Życzę miłego
Pozostajemy,
myślenia.
Karolina, w kontakcie. Dzięki.